Good evening, everyone. So today we have a lot of content to cover. So I'm not gonna wait for everyone for a couple more minutes. I'll just start directly. And just to be clear, I just want to check everyone can hear me, right? That's great. Cool. All right. So let's start. And in the last time we talked about byte and endiness, but we didn't finish that. So today let's start with byte and endiness. I will do a quick wrap up for where we are at in the last time, and then let's start from there. All right, so byte and endiness. Last time we talked about like those bytes. Byte is 8 bits according to the standard, right? And then we talk about the representation of byte. We talk about like how to convert a bit to a byte and how to represent a byte using hexadecimals. So for example, if we have a bit and this is the position, like from the 7th to the 0th. So it's like the way that we look at the digit, right? So if we look at the digit, if we look at a number composed of digits, such as 10, 10, 1100, we always just like think that, like this is the higher bit and this is the lower bit, right? And if we convert that to hex, what we do is that we look at the first 4 higher bits, and then we convert that using a hexadecimal. And then we convert the second half to another hex number. And then we just combine this together as hex AC. And then we know that A is the higher 4 bits and the C is the lower 4 bits. All right, and then we talk about characters. And I want to show you that characters is different from what we have shown from here, like as a number. And the way that is different is in the way that according to ASCII, we know that to represent the character A, we use one single byte, which is hex 61. And starting from there, if we want to convert that to a binary, binary digits, we have the first 4 representing for this digit, and we have the second half representing the second digit in the hex number. However, if we are going to show a string, right, and then this string is composed of 2 characters, A and B, how are we going to represent that? Okay, so we know that for B, it is hex 62. And then for A, it's hex 61, right? And the way that works is that we put first byte in the low memory address, and then put the second byte in the higher memory address. So if you look at the memory, you will see that this is slightly different. And actually, let me just explain this a little bit more. So this means that if we look at the first byte, right? So this is hex 61, and then we know that the lower part is 1. So this means that if we look at the low memory address here, it will first start with this first 4 lower bits, which is 1. And then the second will be this 6, hex 6. And then we look at the second byte, which is B, right? And then again, 2 here is the lower bytes, a lower 4 bit. So this like 4 bit will be hex 2, and then it is hex 6 again. So this is different from things like hex 6162, because byte 2, which is B, is in a higher location. So if we look at this memory, you see that actually because when people like eyeball a number, it always like left is the higher address, and the right hand side is a lower significant bit. So it's actually it's the quite like it's the opposite way. Okay, and then to be more concrete, let's take a look at another example, which is an argument that is a type of integer. Okay, so suppose that we have an integer, and the value of this integer is 1,100. Okay. And the first that we're going to do is we're going to convert that for 4 bytes, because integer is composed of 4 bytes. And in this case, if we look at the memory, we will see this. I is equal to hex for C. And then if we look at this entire 4 bytes, and then now we know that each of the 2 digits here, which is actually hex digits. So each of these two hex digits represent 1 byte. And here this is byte number 1, byte number 2, number 3, and number 4, right? And then when we look at this, you see that in this case, because this integer, and this is the lower significant bytes along with this 4 bytes, right? So here we saw, if we look at the memory, we found that this is what is shown in the memory. And then if we look at the memory layout, which we know that the bytes will start from lower address to higher address. So instead of saying this, if we look at the memory, then it is the opposite, meaning that this bytes, it looks like is the rightmost if we represent it as an integer, right? However, it will be put in the lowest memory. So that is why this 4C will go to the first byte. So here is hex 4C. And similarly, the other bytes will just like go to those, those according correlated location. So this is what is called little endian. And this means that the least significant byte will go to the low address. And this is what exactly is like represented in x86-64. Most of the like the operating system or most of the laptop that you're using right now is x86-64, unless you're using things like M1 like laptop, which is already encoded by ARM. So for x86-64, it will have little endiness, and also throughout our entire section, a section of software security, we're gonna like continue to use little endiness as the endian to show those difference between like this layout, which is different from what we visualized when we look at those digits, those numbers. So I want you to keep in mind that we're doing little endiness, and always is the case that significant byte, least significant byte will go to the lowest address, which is a little bit counterintuitive. Okay. Let me clear this up. Right, and then what if we have a string then? So if we will have a string, it starts with the hex 4C, and then followed by hex 04, and then 2 hex zeros. The way that it works, or the way that it arranges this character, the string was arranged in the memory, is that it will start from this first byte, go to the first byte of the string. So this is actually different from integer, because in this case, it will just like go as what it is. So the first byte in the string will go to the first byte in the memory. And also the second byte go to the second, the third go to the third, and also the fourth go to the fourth. But then if we want to convert this to integer, again, because we're doing little endiness, you want to keep in mind that it's always the least significant byte go to the least significant like the least significant, the lower address. And then also the lower address byte will become the least significant byte in an integer. So you want to make sure that this byte actually goes to the rightmost of the integer. The second is the second rightmost, and so on and so forth, so that we get hex 44C, and then we get 100, 1,000 and 100. Okay, so that's pretty much for endiness, and also for bytes. And this is very important because in the later, lecture, and also in the later on, course assignment, you will use this knowledge again and again and again. Like this is a very fundamental knowledge that you just like keep using it when you try to reverse engineer or try to identify bugs from a vulnerability. So please make sure that you understand this. And if you don't, feel free to ask me questions. Okay, and one more thing. So I know that this is confusing, and we don't really want to do this by hand again, right? Then how are we going to do that? Is there an easy way for us to like use tools or call functions that can help us to convert? And the answer is yes. If you use Python, you can use this package called struct, and then you just like easily do struct.packed, followed by this format, which I will talk about that later. And then this specific number. Basically, you want to convert this integer into least, into the memory, like convert that from an integer to an actual byte or say character sequences with the format of little endianness. And here, small means this is little endianness, and I means that this is an integer, because it's important to know the size of the byte. If the size of the byte is say it's 8 bytes, then you're gonna return 8 characters. And then if it's 4 bytes, then you want to return 4 characters. So it's important to know the type of the argument that you pass to this specific function. So remember again, smaller sign here means this is little endianness, and the type represent and the I represent the type of the integer. All right. And also on the other hand, if you want to convert a byte sequences to an integer, you can use this struct.mPack. You see that this is the opposite of the pack function. And then what it does is that it will return the value sequence according to the format that you specify. So here we pass in 1, 2, 3, 4, 4 bytes, and according to the format, it will return you, a list, and then we extract the first element from the list, which is going to be the integer. And the reason why it returns a list, if you may wonder, is that we can pass in a string that is longer than 4 bytes. It can be like 8 bytes, it can be 16 bytes. And then if that is the case, then when calling unpacked according to this specific format, it will return multiple integer, right? So if it returns multiple integer, then we want to get the integer that we want. Maybe it's the first one, maybe it's the second one, so that we need an index. And this is the reason why here it will return a list. And in this specific case, because we know these are only 4 bytes and we only will convert it to one integer, so that we know that we want to index the list with the with 0 by 0. Otherwise, we want to do maybe by 1 or by 2 if we want to have multiple integers and we want to maybe pick the second or the third of the integers. All right. So far, so good, everyone. If it looks good to you, then we're going to move on to the next topic. So far, in terms of little endianness, is there any question? All right, so we're good. Nice. Okay, so now let's continue. And then now let's talk about different types of variables. Um, you may have already known this in your C class, but just want to emphasize it because we're going to use this information, use this knowledge throughout our session. There are different type. There are character, short, integer, long, or long, long. Um, and the only difference between 32-bit and 16-bit architecture is that for x86-64, which is 64-bit architecture, the long type will have, the long type will have 8 bytes, whereas for 32-bit, the long type will have 4 bytes. Other than that, it's the same. Like a character is always 1 byte, a short will be 2 bytes, an integer will be 4 bytes, long will be 8 bytes or 4 bytes, and long integer will be 8 bytes. And I mean, those things you don't have to really like remember it, but actually the more you use it, it will just like very, very intuitive. It will just like inherit in your head immediately. So I would say like you don't have to spend too much time to just remember it, but as long as you keep using it, you will realize that you will be able to remember it very quickly. All right. And also, I want to say that in our lecture, we're going to focus on x86-64, which is 60-bit architecture. So we're going to use the, or say refer the type as well as the size using this right column of the table. So if you have any questions, you wonder the number of bytes for each type, you want to check this table, and you want to check this table for 64-bit. All right, cool. Okay, so the next that we're going to talk about is reverse engineering. I know that many of you have heard about this concept before, and today we're going to start with something that is fundamental. Before we talk about reverse engineering, let's actually start from the, like, what was the reverse? It has to be like opposite to a order, right? So it's like the opposite of some order. And then today we're going to first talk about the actual order, and then in the next lecture we're going to talk about like the reverse order. All right. And when we talk about the right order, it's actually the compilation process. So first of all, let me know, like, tell me how many of you have heard about compilation, or how many of you have taken a compilation class? And you can just type it in chat. Okay, so some of you said yes, some of you said no. I was like 1/3 versus 2/3. So compilation, like, a course that teaches you compiler, or like, yeah, like for example, semantics or syntax analysis, optimization, like, or maybe a class that just give you even a class that give you a higher level telling you what compilation is. Yeah, I think CSE 340 should count. Nice. Okay, so I see I was like 2/3 of you knows about compilation, but 1/3 of you don't know about that. All right, now we have more no's, so it's like half and half now. Good. Okay, so if you have heard about compilation, then I can tell like reverse engineering is kind of the opposite of compilation, meaning that you're given a compiled code, an executable file, you want to infer kind of like source code or the high level information about this program. And it's okay that you don't know about compilation before, but at least you have compiled some code before, right? Like you may use GCC, you use like GCC, a source code, a C code, or G++, followed by a C++ code, and you compile that to something that is runnable, right? And today, we're gonna first talk about the process. of compilation. Like if like inside GCC, what is going on over there, and then it is actually it is, we can divide it. It is divided into multiple steps, and we're going to quickly go over those steps on a very high level. All right. Okay. So first, again, you know that I have been using binary to refer a program that is executable. And the reason for that is because when we talk about binary, the first thing it should be like the binary number, right? It's composed of 0 and 1, and that's it, right? And then when we talk about a software program, it's essentially just a bunch of zeros and ones. And if you look at that just like this, you will feel that this is just like, doesn't make sense. It's just like very messy. But it's okay, because like you may wonder, how are you going to generate a program with 0 and 1s given a higher level code, which is the code that you normally write, like a C or C++ code. And then I'm going to walk you through about that process. So like this, you're given the source code, you compile that to a file, which is called executable file, or AK binary. And then you run this executable file, you get what you want, your expected result. And then reverse engineering is just the opposite. Like you're given this executable result, or you're given the executable file, you try to infer the source code from there. And usually we call, again, like we call this executable file, call it binaries, or to be more formal, we call it x86-64 Alph executable files. And I will talk about like what Alph means later on. But like for x86-64, you probably heard about that. Like this means the architecture, or say the target of the file. So in this case, it is in the instrument, the ISA, what is called, instruction set architecture, right? Like x86, ARM, MIPS, they're all different kind of architecture. They're all kind of an instruction set. And in this case, it is x86. 64 means that it is in a set of x86, but it's 64-bit, because originally when x86 is invented, it's only for 32-bit. And then later on, people extend that to 64-bit. All right. All right. So first of all, let's talk about compilation. So again, we have, for example, example.c, we have a source code. We compile that. And we can use commands such as GCC. You can also use like your IDE to compile that. But GCC is kind of like a command line compilation. You can just do this. If you have Linux right now, you can just do literally the same. Like copy paste this command, GCC example.c-o, and it will output a thing. You can specify the name of the outputted file, or you can, if you just leave it there, it will be in the name of a.out by default. But otherwise, you can specify that as example.out. All right. And actually, there are multiple steps throughout this compilation process. I would say there are 3 major steps. The first is the actual compiler, which is also called like CC1. And then the second step is to assemble it. We call it assembler. And then the command for that is AS. And actually, if you just type CC1 or AS in your Linux machine, you can still get that. And the third is LD. It's a linker, or sometimes collect to. It's actually like LD has become a integrated and a larger component with collect to. But like essentially, we can consider this as 3 steps. You compile it, you assemble it, and finally you link them. And then for this 3, like this tools for each of these 3 steps, they're called compiler, assembler, and linker. And actually for GCC, we always just say GCC is compiler, but it's, I mean, strictly speaking, it's not. It's a collection. It contains more than just compiler. So that's why like GCC actually is short for the GNU compiler collection. So it's a compiler collection composing of not only just compiler, but also other components, which is essential for this compilation process. All right, and if you want to get those like intermediate files, like you see this 1, 2, 3, those steps, they will have intermediate files. You actually can print them out. You can just leave them. If you use save tabs or add -v, you can get those information over there. And because of the limit of time, I'm not going to show you, but if you just try that in your Linux system, you will be able to get all those intermediate files. It's actually quite fantastic. Okay, so let's start with this one by one. All right, so the first is compiler. Let me see if I can share my screen with you with both the slides and the Linux operating system. Just give me a second. Start with compiler first. First of all, let me start from here. And we can work on this together. So for example, suppose that we have a program and let's just create another directory just in case that I contaminate what I already have here. All right. Okay. So first of all, let's try to do this compiler stuff. And if you do CC1, you see, oh, I need to install it. Oh, it's CC. Okay, yeah. And the reason why it's called CC1 is originally it's called CC1, but here it is CC. Okay, so what we are going to do is we're first of all compile this from a source code to assembly code, and let's try this together. So you do CC followed by the name of the file. All right, so there's some slowdown in my laptop right now. It's very slow. So I'm sorry about that, but it should, hopefully it's not too slow. All right, let's try that. Okay, so we got example.s. And it's .s means that this is an assembly code. And you can just specify that with other suffix, but usually for assembly code, we use this .s to represent that. All right, so let's take a look at it. It's pretty messy, right? You can't understand what it is. If you do example.s, so it says that this is a shared object. All right. And throughout this process, what it tries to do is, first of all, it will do pre-processing. It will do like remove those comments. It try to substitute those macros. Like the first thing is try to digest the source code. It try to digest those macros, those comments, and then combine source codes. If there are multiple source codes, then they will just combine all the source codes into the file. And then the next thing it's going to do is going to compile it. If you have known about those compiler process, this is where it happens. It does like lexical analysis, syntax analysis, try to do optimizations. For example, like that code elimination. Or also like register allocation. So basically, after this process, you will get something that looks pretty like similar to the thing that is executable. And then in the second part, it will convert this assembly code to something we call an incomplete machine code. And if I do this, let's take a look at that example.s-o, example.o. Good, it gave me some error, but that's okay. I have compiled something out before, so we can take a look at that. which is cexample.o. And then if you do file, c-example.o. All right, so it says that this is an Alph file and this is called relocatable. I want you to just remember this is called relocatable right now. And as I show here in the slides, I highlight this relocatable. And later on, you will see that something got changed. It's no longer called relocatable, okay? And let's continue. So the third step is the last step, which is you link this incomplete machine code to a complete machine code. And in this linking process, it will make sure that like the libraries are included, environment are included. For example, if we use printf or if we use like map copy, those kind of library functions, linker will make sure that the program will be able to find those functions correctly. So that when by the time that the program is executed, it will find the printf. And in future lectures, we will talk about how this managed to happen. Like it can go through different kind of ways, and one way is to use a table called global offset table, and we will talk about that. Okay, so this is the entire process. And after we compile the code, if we check this again, like do file, you can get the format of the code, like the out. You found that it's no longer called relocatable. It's called Alph 64-bit LSB shared object was called executable, right? So this means that this is something that is actually can execute. And if you run this, you will get something you want. Like you will get all different kind of output. So this is this entire process. It composed of 3 parts. Although for you, you don't have to know that in details because this is just like one step, one keystroke, one command line, GCC, and then those magic happens. However, it's important for you to know about those essentials because this is like a very fundamental thing for the compilation process. Okay, and then for us, for reverse engineer, we're gonna go that back. So it's like given the executable file, you can run it, you can get some executable result. And given this executable file and executable result, you want to infer the source code. How are we gonna do that then? Right, suppose that you're given the executable file right now. So for you, if you check executable file, what we can do this right now. Like this is executable file. We open it, we just use them. We see that there are some strings that looks readable, but most of them, it's just like random characters. You can't even visualize it using like editors such as Vim. You can do it a little bit if you do this hexsd, meaning that you just convert the actual like visible characters to hex. So you just show those, show the file by hex. And here, this part, it just means the offset of the file. And the middle, those middles, these are the actual bytes inside this file, which is a.out. And the right-hand side just show, like visualize those bytes, if those bytes are characters that can be visible, okay? All right, so then how are we gonna parse executable file? How are we gonna parse, like an Alph file in order to understand the actual content? Or put it in this way, when a computer reads or a computer executes an executable file, how does the computer manage to understand those nulls and zeros and ones so that it knows what to execute? And this comes to the format of an executable file. Alph binary, which is the binary that is executed for Linux operating system, is short for executable and linkable format. And usually, if you look at this Alph file, it composed of 4, I would say like 4 major parts. Okay, So the first part, we call it Alph header. I will show you later on. And the second part is called program header table, or it's called a segment table. And then the third part is the sections, like the actual program, the code instructions, they're stored in sections. And sometimes their data, like uninitialized or initialized global data, they're stored in sections. And then the final one is called section header table. And later on, I will show you like all different kind of tables. This format by parsing the Alph in front of you, we're gonna do that together. And also I will show you why it is necessary to have those four parts, how those four pieces come into play so that programs will be able to execute its property by a computer. Okay, and so far, is there any question? No? Good. Cool. Okay, I'm gonna continue then. So Alph format. Let me skip this because we already showed that. And then this is the part that I just talked about, right? And let's first start from Alph header. So Alph header is the first part of the program. And what we could do is that we can use read Alph to read the Alph, like read an Alph binary, which is in this case a.out. If you do that, you will find there are many options. And then let's first start from, let's see. Let's first from headers. Let me see from the Alph header. And then let me check the commands. Okay, so it should be the second one. Display the Alph file header. So let's do that. H followed by a.out. Okay, so this is what is shown for the Alph header. There are many fields over there, which is fine. I will explain that to you. So Alph header contains like the overall information about an Alph binary. And also it's kind of an index, or say like a contact information content table, like a content table for a book. So it's like you open that, it shows at the beginning, and then it will tell you if you're gonna find a specific part of the program, go look at page number something, or that just like in this case, there's no the notation of page in an Alph binary, but instead it has this memory, or say the byte offset. So it will tell you that if you want to find these things, go to offset number something. All right. So first of all, you see that there's a magic number over there, but also it has some information. So it will tell you that like for example, whether or not this is a 32-bit or a 64-bit Alph binary. It is, for example, here, Alph 64, it tells you about that. It also tells you information such as where is the start of the code, which we also call an entry point. So it tells you which is here, entry point address. So it tells you, or say it tells the computer when the computer reads this Alph binary, it tells that if you want to start to execute program, start to like execute those instructions, then go to this offset. And now let me open this up, and then we can work through over here. Sorry, let me retype. All right, so for example, it says that the entry point, it says give you this information of the instructions set architecture, and also it tells you the location of the so-called program header table and section header table. And let me run off this K in this tab so that we can compare what it shows here. When we read this Alph binary byte by byte, and also show this extracted information using tool read Alph. Okay, so if you see the slides, you see that this is the same as what I'm showing over here. And then the only difference is that I'm showing more bytes in the Linux operating system in the terminal, whereas in the slides I only show the first 1, 2, 3, 4, so it's the first 64 bytes of the binary. Okay, so let's do this one by one. Or not really one by one, but like some information that I think is well worth to note. For example, you see the first part here in the terminal. There is a key value, key number, hex 2, hex 1, and it has a specific meaning according to Alph format. So hex 2 means that it is a 64-bit here, 64-bit binary. And then 01 means that this binary goes for little endedness. So which is something that we just mentioned, right? Little endedness. And then followed by that, if you look at this part 30, you see there is a number 4000. So it's here. So it tells you that the size of this current Alph header, which is 64 bits, because here you see that this is 40. And this means that this size of this header is 64 bytes. Okay. And then continue. There is entry point. So you also see that from here, if we parse the information, extract that using read Alph, it tells you that where the entry point of the program, but also you can read that if you have know the offset in the Alph header. So here it's going to be stored in the 18th hex 18th byte, starting from hex 18th to hex 24th. And then this is, you see that this is 3006, but remember that we're talking about little endedness, right? So for little endedness, the least significant byte go to the lower address. So this is the lower address, if you remember, right? So this is lower address, and this is higher address. And that is why, if you look at this 3006, in your mind, you should parse it in a way that this is hex 30 and then 06. And this is what you got, right? So this is the actual starting address for the instructions, like the instructions that the program will be executed. All right, and then let me clear this up. Let's continue. And another information is about the start of program headers. So usually the program, or say the computer, it will start with reading the Alph header, and then starting from the Alph header, it will tell you where the other part is inside the Alph binary. So in this case, the start of the program headers, it's it stores in this location, right? And then again, because this little endedness, which is very important, that's why I want to talk about that before we talk about all this Alph binary reverse engineering thing. So we know that this is, it looks like 4,000, but actually it's not, because again, we want to do little endedness. So it's gonna be 40000000. So that is the offset of program headers. And later on, we'll talk about program headers. Write this a little bit better. Hopefully, it's not really makes it more messed up. Okay. And also, as it shows over here, so for the 30s byte, there is another one, right? And that is the size of the program headers, like these 2 bytes. And again, little endedness. So when you see 30 or 38, that is the least significant byte. So it is hex 3800. So that is the size of program headers. And that is equal to 56. So that means that each item in the program header occupies 56 bytes. And we will go over that later. All right. And then again, it has the size of section headers. Again, it is little endedness, 64 bytes. I'm not going to go into the details. Okay, and now it comes to program header, which is also called segment header. So in this part, program header, it instructs the computer to create a process image. And later on, we'll talk about program execution. Actually, when program is about to execute, the program, the Alph binary, will be loaded into the memory, right? And the way that it loads into the memory is according program headers. So program headers tells the computer that, hey, you're gonna load all those necessary information, like those segments, which is cut into segments, you will load those into your memory. And this is the right address that you want to load to. And those are the offsets to the base of the address. So for x86, there is a fixed base address. For x664, depending on whether or not you're using you're using like a specific how to say, like the defense mechanism, or depending on whether or not you're using debugger, the base address may change, but that's not important. Right now, I just want you to know that this basically tells the computer that if you're gonna load the program, the Alph binary into the memory, then this header, program header, is gonna tell you where that you should load it to. All right, and then here you see that for program headers, it's a table. It's a table composed by different items. There are multiple items over there, and I'm just show here in the slides 3 items. There are actually more, and let me show you here. We can still use read Alph and use the command of -l. We can get this headers, program headers. And also, if you look at the upper part, if you look at the actual bytes in the binary, you will, it starts with hex 40, right? Because according to the previous, the Alph headers, it says that it will start from this particular place. And then for each of the items, so it's here in the slides, for each of the items, there are multiple like fields representing a specific header. There is offset, meaning that where you want to load it to. And there is the virtual address. Also, it's about like when this when this header loads into the actual memory, the virtual memory, this is the address. So the first offset is the offset inside the Alph binary, and the second, which is virtual address, that is the offset that you want to load it to. And then third is a physical address. The fourth is file size. It means that this is the size of this specific part, like this specific segment. And then the memory size usually is the same. It's also like if you're loaded into the memory, then this is the size. And then flags, which is important, means that for this specific chunk of maybe code or data or whatever, but like for this specific chunk, if that is readable or it's writable or it is executable. And in this case, it has only R over there, right? And this means that this is only readable. And then alignment, this means that when you load this specific part, like not like load that part, like starting from hex 40, with the size of 1F8, we'll load it into the memory. You want to make sure that the memory is aligned with hex 8. Okay? And then those information, they're actually all maps from the byte here. So for example, in this case, hex 6, this maps with the type of the header. And then hex 40, this maps with this readable. All right. And then followed by that is the address. And this is another address. And there's another address, like you just go this one by one. And then it is the size. It is the mem size. And I believe that's it. Oh no, and also alignment. So this is the alignment. So here you see I am underlining 1, 2, 3, 4, 5, 6, 7. 7 parts. And if you add those together, there are 7 parts times 8 bytes, right? So it is 8 bytes times 7. That is 56 bytes. And if you still remember, in the Alph header, we have that each of the program header item is 56 bytes. So this is like maps perfectly together. And all the information just represent this in the similar way, one by one, so that we have the entire items inside the program header. All right, so far so good. Any questions? Good. All right, then let's continue. So as I said, those items, they're called segment also. And this is why program header tables sometimes also called segment tables. And what is a segment, right? I will talk about it later. But now let's just continue to talk about another term, which is called section. So besides segment header tables or segment tables, there is another called section headers and section table. So those headers inside the section header tables, they record each section. And also they have the specific meaning. They said their size, their name, whether or not their type, their flags, like size, all the informations. But I'm not going to talk into the details about those sections. But if you look at this on the high level, you see that we have headers, and then we have program header tables, which we just talked about, right? Those segments, and we have section header tables. And actually, if you look at those information in section headers, they point to something also to this part. So if you look at what I'm showing here in this table, there are some like arrows, right? And there are also other arrows. So it's like section, there are, finer granularity composed to segments. And in fact, if you use readelf-l, you will see that usually one segment mapped to one or multiple sections. And there is a section to segment mapping. Okay, so it's like each of this, they are a section, and each of this on the left hand side segment with the number 0, 1, 0, 2, etc., they are segment. Okay, and this is basically how it looks like for Alph. Right now, you know that Alph binary or something that is executable is no longer mysterious. Actually, it's well structured with specific format, and with many comprehensive like fields connecting them together, linking them or pointing them to different parts of the program. It's actually a very nice structure so that the program, like the computer, when it is executing the program, it can parse those formats and understand those necessary information so that it will know how to execute a program. And then now let's talk about execution. So for a computer, when a computer executes an Alph binary, from the executor's perspective, it's different from the way that a program was compiled. Actually, when a program is compiled, then it will go to the right-hand side part, basically. That is also what is called a linker's view or linking view. So it's like the compiler and the linker will put up those code and data into sections, and then it will use the section header table to represent where are those codes or where are those data. However, when a program is going to be executed, the computer will use the loader, or say the computer will like look at the program from an executor's perspective. When it looks like that, it will ignore the section header table. It will look at the program header table to get those segments, and then it will load each of the segment into memory. And they're actually the same. If you look at the code and data, segments is essentially the same as segments, just the way that they separate those code and data is different. And then the way that the computer looks at the program is different. By the time that they execute the program, it will be different from the time when it compiles the program. Okay, and now let's talk about the actual execution process. So the executable is invoked by execv. So this is a system call, and what kernel does with that is that the kernel will load the executable into memory by program header table. So let me just go this back again. The computer looks at the program header table. Sorry, just give me a second. The program will look at the program header table and use that as an instruction to load each of the segment into memory. Okay? And then after it loads into memory, and then look for this entry, it's called ptinterp, which if you look at the right-hand side, like this parsed program headers, it is the second one, interp, to find the right, which is also called interpreter, to interpret. Okay, right, it's here, right, to interpret the program, but it's different from the Python's interpreter. This is more of a dynamic linker. So it tries to locate the dynamic linker, which is specified while it is compiled. Like if it's specified in the program header already, it tells the program, it tells the computer that, hey, if you want to get the rest of information, you have to get the right linker to do the rest of the work. And in this interp specific field, it tells it. Actually, if you look at that interp, you see that the offset is hex 238, right? And then let's go to this place, 238, in the actual Alph binary. 230, okay, yeah. So 238 starts from here, right? And you see that it's a readable string. This is exactly what is stored in your header file. So it tells you that if you want to find what is where linker is, then go to this address. And this address tells you that, okay, so the path of the linker is at /lib64/ld Linux x86-64.s0.2. It gives you a very a complete path so that you know where you want to find your dynamic linker. And then the next is that you're going to dynamically linking the program. You're going to map the shared library to the program's address space, for example, libc. So it's like you use printf, and then the printf belongs to a shared library such as libc, and then you just want to map libc to the program's address space so that the program will be able to identify where, say, printf is, right? And then it will relocate the text and the data of the dynamic linked library into memory segment. This is why, if you look at the program without linkers called relocatable, means that those are the compiled like code, and then you can relocate that according to where the library is. And then in the end, it will relocate the symbols of the executable referred to the dynamic linked library. Okay. For example, shared library, as I said, libc.so. And for example, you have a function that you want to call, the program want to call, which is printf. So, the loader or the computer needs to load libc.so, which is the compiled library, the library that is compiled, that it contains the instruction of function printf into the memory process. So you may ask, what if there are many executables using libc.so, which is pretty common, right? For example, you run two programs, and then both programs, they call a printf. So do you want to just load it again? Do you want to like load it, like copy paste the entire libc into a memory and then do that again? And it's very likely that you don't want to do that because it's just too expensive, right? So the way that it works is that it will just check if the library already in the memory. And if it is so, then just map that memory to a new process space. But if it's not, then you need to load and then put this like libc.so into the actual memory. And so that in the future, if there is another process going to call libc.so, depending on that, then we can do this same process. Okay, and then the next is we're gonna look up the program entry. So here we already show that the entry point is 630, right? So if you do re-elf, you can get that from your elf header. So let me go back again. And then it will start to execute the program as what it is. Okay. And then you may wonder that how are we gonna get those like information? How are we gonna know where something was loaded to somewhere? And I'm gonna show you two ways to do that. But before that, let's talk about like how we're gonna find those dependent shared library. So what you could do is you could do LDD out. So LDD followed by the executable file. You will see that, okay, those are the libraries that this program needs. So, sorry, we found that there are three over here, right? And then also there is a specific address, like those are the virtual memory address for this binary. If the binary wants to like read the information, get the information about those libraries. Okay, and the second is, as I said, you want to get the virtual address mapping into an actual executable, and then we can use. There are two ways that we can do. One is that let me exit it, and one way to do that is to use GDB. I think it's very likely that our lecture will require you to use GDB heavily. So if you don't know GDB, you probably want to catch it up very soon because later on we'll be using that very heavily. But if you already know that, that's great. So you want to do GDB, which is a debugger. It's just like a command line once debugger. So you want to do GDB 8.out. And then you want to set a breakpoint. I'll just set it in the main function. Okay. And I'm going to start to execute it. It will stop at the main function. And then we're going to do VM map. I will show you all the memory address, like memory mapping. you see that this is 8.out, where is 8.out is maps to. And the reason why it shows in red right now is because this means that there's code from this address to that address, and their code, like those the actual instructions. And then this part is also contains the read-only data. And then you see that from 500 to 600, they're the data. So they're not read-only data. Those are the data that can be editable. And then followed by that, you will see that this is the instructions for libc, right? And then this is the instruction address for LD, which is another library, which is the interpreter will say the dynamic linker. And there's another dependencies. Oh, this is the code part of the dynamic linker. All right. So this is way number one. If you're using GDB, then you can do that. There is another way, which suppose that you are running, like this current binary is running right now. So if the binary is running right now, then you want to inspect the memory of this running binary. And in order to do that, you first need to know the process, because when a program was run in the operating system, it'll be run as the process. So you first want to know where is the ID of the process that runs this specific binary. And what you do is you could use PID off. This is a command in Linux, and then followed by the name of the executable. Okay, so in this case, there are two, because I have another tab. You see here, I have another tab that is running GDB, running this program as well. And then let me just exit that. Okay, now let's do PID off again. See, there is only one now, which is the one that is running here in this panel. Okay, and then next, what we could do is we can use pmap, which is also command in Linux. And then you want to use pmap followed by the ID of the process. So in this case, it's 125308. And you can get the memory address as well. And you see that this is identical to this one, although this one is not visualizing it in a prettier, like in a pretty way. This one has color, has legend, but this one is more of like a plain one, but it's still readable. Okay, yeah, so that is pretty much for what we have today. So as a recap, today we talk about Alph format. We talk about how a computer identifies the content, or say how computer understands a Alph format binary, Alph format executable, so that the computer knows what to load to the memory. The computer knows how to execute a program from a start, where the start is, right? So we talk about this format, and then we talk about the process, first from the source code to the actual compiled executable file, and from like the process that starting from the computer loads the executable file to the moment that the computer is about to execute the instructions of the program. And then starting from our next lecture, we're going to talk about the actual instructions that will be executed by a computer, which is the assembly. So in our lecture, we're going to focus on x86-64, and I will give you a like instruction or like an introduction about how to understand the x86-64 assembly, what are the resources, and then what is the common structure for x86-64 instructions. And then in the future like assignment and in class practice, we'll be very likely to read those assemblies. So if you don't know what they are, I highly encourage you to get some sense about that, just like Google it to take a look at it very quickly so that, just like learn ahead of times is in case that you need more time to digest that. But if you already know about that, that's great. Just take your time to maybe review it before you really need, like you really read them line by line, instruction by instruction. Yeah, and then that's it. And then give you a little bit teaser, like this is just a heads up for what we're going to talk about for x86-64 assembly. We're going to talk about like different kinds of instructions in different structures like this. And then like register, what are registers? Those registers, what does it mean by push, like the stack, what it means, these instructions, etc. Some syntax, some operands, and then like more instructions. But I'm not gonna give you like the entire, like the way that you read C, like the way that you learn C, like those are all the operands, those are all the registers, etc., etc., etc. Basically, I'm gonna give you a high level introduction about how you're gonna read disassembly, how you're gonna read or say it assembly, right? And then starting from there, you probably need like a tutorial or like a handbook for you to refer. You need to maybe like look into those mnemonics to a reference or like a code book for x86-64, like MOV or ADD add or SUB subtraction, right? So you want to have, if you want to have a comprehensive understanding, you probably need something like a dictionary. But I'm going to tell you, I'm going to teach you how to use this dictionary to understand the languages, which is x86-64 assembly. Okay. And that's pretty much for today. And that's pretty much for next lecture. More questions? If not, then you're happy to leave. I will stay here into 7:15, so it's like in 2 minutes, just in case that you have any questions. Otherwise, see you in the next week. Bye.